Hello everyone, I'm Professor Harrison, and welcome back to our module on statistical inference. Today we're going to be covering the significance level and the decision rule. In the last video, we learned what a p-value is. It gives the probability of your result under the null hypothesis. Today we're answering the follow-up question. Once you have a p-value, how do you decide whether it's small enough to act on? We're following Bess, an investigative journalist on a cold case she can't let go. And today she's working a case involving a commodity broker suspected of front-running client trades. The broker ended up on the profitable side in 30 out of 50 observable trades. Bess has already computed the p-value and it's 0.08. Now she needs to decide what to do with it. She pulls up her case file. The p-value is 0.08. That means that if the broker had no advanced information and is basically guessing on every trade, then there's an 8% chance of seeing a win rate this high or higher by chance. That's useful, but it doesn't tell Bess whether or not she should publish a story on this case. She has a number, but she needs to decide a threshold where she decides that she has enough evidence to publish her story. That threshold is what we'll call the significance level. The significance level, written as alpha, is the cutoff you set in advance. If the p-value falls below alpha, then you reject the null hypothesis. If it stays at or above alpha, then you fail to reject. The decision rule ends up being exactly that simple. Reject if p is less than alpha. The most common convention is alpha equals 0.05. That's been the default in statistics for close to a century. But there's nothing sacred about 0.05. It's a convention, not a law of nature. Fields where the cost of being wrong is very high, things like medical trials, structural engineering, often use a stricter significance level, something like 0.01 or even 0.001. Exploratory work, where you're looking for leads rather than conclusions, sometimes use 0.1. The right choice depends on what's at stake. There's one rule that is non-negotiable though. You have to set alpha before you look at the data, not after. If you run a test and see that the p-value equals 0.06 and then decide that your threshold is 0.07, you haven't done inference. You've just forced your data into a conclusion that you want to see. The whole point of setting alpha in advance is that the threshold is fixed before the result comes in. So let's apply this to the broker case. The p-value is 0.08. At alpha equals 0.05, 0.08 is above that threshold, so she fails to reject the null hypothesis. The evidence doesn't clear the bar, at least not enough to publish. Now, if Bess really wanted to publish this story, she might be tempted to switch her threshold to 0.1. And since 0.1 is above the 0.08, that means that she would reject the null hypothesis instead, and the evidence would in some sense clear the bar. But the problem is that she can't decide to change that threshold after she's already seen the data. Doing so is simply forcing a conclusion, not doing statistical inference. So with the same data, the same p-value, you can end up with two different conclusions depending on what the threshold is that you chose. That's not a flaw in the framework, it's kind of the whole point. The significance level is a choice about how much evidence you require before you're willing to call something real. And that's exactly why we need to decide it before we ever look at the data. Now, alpha has a direct statistical interpretation. Alpha is also called the type 1 error rate. A type 1 error is rejecting the null when it's actually true, so calling a pattern real when it's actually just noise. If you set alpha to 0.05, then in 5% of the cases where the null is actually true, you'll end up rejecting it anyway just because of random sampling variation. You're not eliminating false positives, you're setting a ceiling up on how often you're willing to make them. So choosing alpha is really just choosing how often you're willing to be wrong. A tighter threshold means that you have fewer false positives. But a tighter threshold also means you'll miss more real effects that barely don't clear the bar. We'll dig further into what this exactly means later on, but that trade-off doesn't go away. And how you deal with that trade-off determines what kinds of mistakes you're willing to live with. In her article, Bess explains things to her readers. Every statistical test requires a threshold, not because the threshold is natural, it isn't, but because the decisions require a line. Researchers have settled on 5% as a convention. It means accepting that 1 time in 20 you'll call something real when it isn't. That's not a small number either. The broker in this case clears the bar at 10%. At 5%, the evidence isn't quite there yet. So the same data, two different numbers, and the threshold would decide whether the broker ends up getting in trouble with this article or not. Given the lack of evidence, Bess decides not to publish the article. Instead, she turns to a case she's been working on for quite some time. She's analyzing a company called TRQ, a hedge fund with an incredible history that may have been using some underhanded tactics. She's been running all of her tests at a 5% significance level. That's her standard. So she goes to look at data, which showed that there's a p-value of 0.07 that TRQ have been taking advantage of a different hedge fund called Callaway Value Partners. But at 5%, that doesn't quite clear her bar. So she decides that there's not quite enough evidence to figure out what's going on with that story just yet. She'll have to keep her eyes peeled to see if more evidence comes in the future. So that's the significance level and the decision rule. You choose alpha in advance. You compute the p-value, and then if p is below alpha, you reject the null. If p is at or above alpha, then you don't. The most common convention is 0.05, but that's a choice, not a requirement. And alpha is directly interpretable as your tolerance for a type 1 error, which is the probability of rejecting the null when it's actually true. Lower alpha means fewer false positives. It also means you end up missing more real effects that barely don't clear the bar. How you set that threshold depends on what's at stake.